Hello everyone, we are ready for another Solana update and this day I have found three articles I found very interesting, three contributions so we have SVM Execution Economics from Toli, WTF is Stakenet, so Stakenet from Buffalo, Lucas, Jito Labs, Validator Economics from Ryan, and let's go, let's start. SVM Execution Economics. It's another blog post from Toli again on Sollinked. You can find it there. It's now available for everyone. And the idea is to talk about what's going on with the fee market in Solana, how it's going to change, how was it in the past, how it works now, how we can improve it. That's the idea. So it's a very nice article, and it starts with the background, like how did it work in the very beginning in Solana. So yeah, at the beginning there were no priority fees at all. So only base fee, well, like a flat fee model, 5,000 lamports per signature. And the idea back then was that transactions were supposed to be, or at least most transactions were supposed to be like simple transfers, and charging in for the number of SIG verify computation it was enough to basically charge the fees. So 5,000 lamports per signature. And well, actually, there was something else on top of that, depending on the network congestion, because there was also a target capacity at a certain level. And if the capacity after that amount was going to be 50%, so reduced by 50%, then the price will double. So there was that kind of mechanism. That was the belief. But this didn't really work, and it's mainly because of two reasons. One is the transaction complexity actually increased fast. With more programs and more composability, you have more complex transactions. They're not just simple transfers, and then it really at this point it's not realistic to believe that we can just charge per signature. We have to look at something else, like transaction complexity. So there was that. And the other problem was that there was absolutely no way to isolate state. So now Solana is like one of their value proposition is that they can have localized fee markets, and we'll see a little bit more in detail how it actually works. But back then there was nothing like that. So all the applications were charged in the same way. And if you have one application with very high demand that increases the capacity, like increases the load on the network, then all the applications would have higher fees. And that doesn't work. That's the problem. So the summary of what is the fee model problem. If the fees, the fees in Solana are a spam prevention mechanism. That's the idea. And not only in Solana. That's a big reason why we need fees, if not the reason. So if fees are too low, then they're useless, because you will just, you're not discouraged by spamming the network, either because there is an economic incentive, like you want to capture some opportunity, or you just want to attack the network. I mean, there is that. And yeah, if fees are too low, you have this problem. If fees are too high, because there is an application that actually requires a lot of, has a high demand, requires a lot of network capacity, and then drives up the fees with this mechanism we discussed earlier. There is a problem for all the other apps that don't have this kind of equilibrium in their economy. They don't need that much activity, and so the fact that the fees increase for them is a big issue. And so what will actually happen is that this application will deploy their fork of Solana. So you have these app chains based on SVM because the fees were too high. That's a problem. And this is a problem for all kind of integrated blockchains. Like this is an actual problem, and the only viable solution, this I'm quoting, is a system that can selectively increase fees. So you need to find a way to increase fees only for specific applications that actually require this very high load, and let the other applications that don't need that high load to keep going with low fees. That's the only viable solution for integrated blockchains. All right, let's see what's next. So this was the old model. One improvement that has been executed and implemented, this what you have now, is having execution priority fees. So in this new model, now users can offer, when they want to have their transaction included early enough, even if there is a highly congested state and they know there is a lot of demand for that specific account, that specific application, and the users want to get included earlier than others, what they can do, they offer priority fees. Cioè, they offer a tip, and the tip is done through priority fees. Tip to the validator. This tip is charged per compute unit, so this CU term now we have, because now there is a way to assign compute units to transactions, and it's a way to meter the complexity of the transaction. So a transaction that is more complex will have assigned more compute units. The compute units are used to charge the priority fees, and also there are compute units for to impose a limit of how much computation, how much compute is required per block. So there is a max CU limit per block, for instance, 48 million CU. I think this is what we have today. So you cannot have more transactions than, or like the total amount of complexity of the transactions in the block cannot be more than 48 million CU. This becomes, the block at this point is considered full. It's like a gas limit, you know. And then there is also, interesting, max CU limit per account write lock per block. So a subset of this 48 million CU, like, I mean, it's a fraction of this 48 million CU, let's say 12 million CU. This limit is the maximum amount of compute units that can be used to touch a specific account or like a specific application. So this model now achieves parallelism and some form of local fee markets. Parallelism because, you know, one application alone will never be able to saturate a block completely. At most, with this account, you have 12 million CUs that are used, and the other applications can use the rest of the resources of the network. And also there is some form of local fee markets in the sense that it makes sense for you to increase your tip, your priority fees, if you care about a specific account that you know is congested or it's in high demand. If you don't want to touch that account, then you can keep your priority fee low or even no priority fee. So this kind of works. And actually, we have, you see, we have data to say that it works, because we can see this Solana Compass, it's actually very nice dashboard. You can see some results they've just taken right now. I've taken a screenshot of what you have. And we can see, for instance, the difference between the minimum priority fee and the maximum priority fee. And you can see this is over the course of 1 hour that there are times in which some transactions need a high priority fee. So you can see there were transactions with a very high priority fee, but still there were transactions at the same time that could get in without any priority fee. This is 0 or near 0. And if we look at the total fee, so not just the priority fee, but the fee in general, and we see the mean fee, or the average fee, and the median fee, we can see that there are times in which there are some demand spikes, and these are clarified by the fact that the mean fee goes high. Why? Because there are some applications, some transactions that had a very, very high fee. And at the same time, the median fee stays low. So this is telling you that at least the bottom 50% of the transaction fees were very, very low during this time, despite spikes in demand in certain applications. Good. Next, yeah, right. I said the localized fee markets are there. I mean, let's say it's a first implementation, because I think when someone thinks about localized fee markets and doesn't actually know how it works in Solana, one might think about an end state like a really complete multi-dimensional fee market where every dimension is an account. and every account has its own EIP 1559. And it doesn't work this way. And there are reasons why. So it works as we discussed earlier. There are reasons why it's still not ideal, and there are issues. But the results are there, so it's good, but it can be better. That's the idea. And the current model doesn't eliminate DeFi spam yet, not completely. And why? In short, because the priority fees, in the way they work today, with how the scheduler in Solana works today, they're still not 100% reliable in ensuring earlier execution. So let's say that you see an arbitrage opportunity and you want to make sure that you capture it before all others. It would be nice to know that if you offer a priority fee that is high enough, you will get in earlier than all the others. But that's still not entirely true. And yeah, let's not go into that in this video, but I will post a link to that explains why that's not the case. It's about the scheduler and it's about jitter in the scheduler. So yeah, it can be explained. But yeah, what was I saying? Yes, since they're not 100% reliable, there is still some space for spamming. So if the priority fees are not 100% reliable, you can just try to just spam and send many transactions to try to capture the arbitrage bots, to capture the profit with your arbitrage bots. So what is the solution? At this point, what we actually really need is a way to directly, reliably increase fees for highly contested state. So really go targeting the contested state and increase the fees for the specific state. So something similar to the really fully multidimensional EIP 1559, where each account knows what is the load, what is the demand for the specific account, and the fees to touch the account go up if there is more demand. That's the end game for the fees. And indeed, in this blog post, there is something like that, and it's called write lock fees or dynamic write lock fees. So here you will have this a proposal, or anyway, it's a research direction to charge transactions depending on which accounts they want to touch. So now it becomes explicit, the localized fee market. It's not like an emergent property, but it's really coded that the accounts that are more in demand, they will be more expensive to be touched. It's really done explicitly. So dynamic write lock, meaning modify, change, touch the account dependent on usage and demand for the account. So here there is a proposal on how to do this, and basically each account can keep memory. You can store information on how much it was used, so how many compute units were used to touch this account, meaning that there were many transactions trying to modify it, so a lot of demand. And if this value, like CU used per block for this account, goes above a certain threshold, then the write lock fees go up for that specific account. And if it goes below a certain threshold by a certain margin, then the fees go down. So dynamic adjustment depending on demand. And for this write lock fees, sorry, 50% of the write lock fees would be burnt, and the remaining 50% would go to the account itself. So there is that. That's another story. And the last point is to have dynamic base fees rather than static base fees. So this will be another change. There is a reminder, this is good to know why base fees are even there, why can't be zero, and that's because you need an incentive for validators to vote consistently and not trying to do weird things or thinking about what is profitable or not. You need something like this. But the innovation that is discussed in this blog post would be to have, again, an approach similar to EIP 59, but for the base fees. And yeah, the base fees will go up or down depending on demand, and there will be a burn mechanism. Okay, so that's it for the SVM Economics. Let's go on. So well, WDF is Stakenet, Lucas Bruder, Buffalo, Jito Labs. And yeah, this was very interesting for me to read because, yeah, I already knew about Stakenet because I was there at Breakpoint where it was announced. Very nice presentation. And that was focused on the first application that was Stakenet for liquid staking protocols and for Jito Sol. But in this blog post, the idea is to go beyond the initial application and define Stakenet is in a more generic way, and also think about potential further applications after liquid staking. So that's why this was very interesting to me. So the blog post starts with a generic definition of Stakenet that is defined here and really just reporting the definition. So Stakenet is a new primitive for Solana that allows one to build autonomous, decentralized programs that allocate resources across a network of node operators. So, what is Stakenet? Stakenet is the way to distribute autonomously um, resources in a protocol that yeah, relies on distribution of resources. Sorry. So, you want to have like this on-chain logic that is able to autonomously read some state or some condition in this decentralized network. And this autonomous decentralized program will be able to go from the state to an action that is distribute resources across different actors. And this is something that happens for Solana liquid staking protocols. Liquid staking protocols is what they do is to distribute resources, but they don't do it in a decentralized and autonomous way. And decentralization matters actually. We don't do this for fun, or we don't do this for for the intellectual challenge. It's actually good. It's actually useful because it reduces risks. And this blog post goes through this, and yeah, I found it very convincing. So, according to Lucas, this is not just for liquid staking, even though liquid staking is of course important, but there are other ideas like applications for restaking protocols, liquid restaking networks, Oracle networks, and more. Nice. So let's talk about the first application because it's how Stakenet will be live and operating for liquid staking protocols. There is a real reason why. So again, what is the problem here is the centralization in Solana liquid staking protocols, on-chain liquid staking protocols. How do you do on-chain liquid staking on Solana? You use a specific program. This is SPL Stake Pool program. The program allows you to deploy staking pools. Now, the thing is, this is not just set and forget. It's not like you deploy the program and you're done, and the program can be immutable and yeah, you're done. No, because there are changes needed for the stake pool. The stake pool must be managed, so someone needs to do operations to modify the stake pool. And like for instance, you need to update the list of validators because maybe some validators stop working, or some are malicious or whatever, the list of validators is not immutable. And also, stake delegation to the different validators in the pool cannot be just immutable. You might want to have some logic to decide how to distribute this stake delegation. So how is this done today? There is a staker authority in the staker pool program that can implement these changes. And typically, the staker authority is nothing else than a hot wallet operated by an off-chain bot developed by the team that created a liquid staking protocol. And this off-chain bot relies on some off-chain data, again managed by the team that handles the liquid staking protocol. And based on this off-chain data, the bot decides how to modify the list of validators or the delegation distribution. This is centralized, so because you rely on a team, and also it's not very transparent because the off-chain data, it's not necessarily clear what is the delegation logic. So Stakenet improves these three components, and you go from off-chain opaque data to more transparent validator history program based on on-chain data, where you will have on-chain the information on validator performance, on who these validators are. So these things will be on-chain, and people will be able to see what is the data that is being used, what is the delegation strategy, and so on. So very nice. Then the staker authority, instead of being just a hot wallet, will be delegated to an on-chain program. It's called here the Steward Program. And this will be the program in charge of using this on-chain data to modify the distribution of the stake, to include more validators, to exclude other validators. So it's a program and not just a hot wallet that does this. And then the last point is replacing the off-chain bot that calls the staker authority in the old case with the decentralized keeper network that instead will call the Steward Program. Or no, the validator history program. This, you see it here. Okay, so let's talk about the validator history program. The validator history program is the one that takes care of writing the validator history account, meaning that this is the program that takes care of having on-chain up to 3 years of validator history information. You need this data because the point here is to be able to autonomously or automatically, depending on on-chain strategies, assign resources, in this case stake, to different actors according to certain strategies. And to do that, you need some data, and this data must be on-chain because then the strategy will depend on these properties in this on-chain data. And this is done by the validator history program in a way that is automatic. Well, you need to have the keepers, so we'll talk about this. Transparent, because people will be able to see what is the history, what is the data that will be used by the Steward program, and governable. So, and there is also that, because governance can decide then which data is important, for instance. The way to allocate stake depending on different criteria. We will see in the Steward program, for instance, some examples. So we have this decentralized keeper network, and here there is, of course, a question on how to decentralize it, if you need some sort of crypto-economic security, like a token for incentives. But let's say there is this decentralized keeper network, and what they do, they call this validator history program that reads from the vote account, and this is a very important point. A nice thing of Solana is that the information on consensus is immediately available to the SVM. So you actually know there is on-chain data on the performance and on the behavior of the different validators. And this is a lot of very useful information that the validator history program can read from the vote account to write the validator history account. Because, as you know, all the voting in Solana, it's actually done through voting transactions. And people sometimes complain, the TPS is inflated, so many transactions, they are just votes. Yes, they're just votes, but it's good. In this case, it's actually very useful to have these vote transactions, because then you can get this information on chain on how the validators behave. And this is then very useful for Stakenet and to have a very stateful validator history account. Now, Stakenet and validator history program will also get data off-chain. I mean, there will also be off-chain data uploaded to the validator history program, and this is done querying by being part of this peer-to-peer network or getting data from the peer-to-peer network of the validators, because there is some important data that you just don't have on chain, and it can still be useful for the Steward program. And this is something like IP address or any way to know, for instance, where the node is located, if it's using a specific data center or not, because all this information will be then potentially very useful to distribute the stake in a way that helps with the decentralization, because you want to decentralize also geographically, also for a number of data centers. You don't want to rely on any single point of failure. So this kind of data, you get it off-chain. I mean, from off-chain resources. But it's not that bad because this data is cryptographically signed by the validators themselves. So it's not just like a random trust me bro model. Okay, then we have the other program, main program, that is the Steward program, and that's the program that replaced the Staker Authority, or replaces the hot wallet in the Staker Authority. And this program is actually based on the information in this validator history account, decides how to distribute the resources. In this case, the delegated stake. Okay, so again, what is nice here is that this happens in a transparent way. The strategy is clear, it's based on data that is public. Most of it is coming from on-chain sources. Everything is very verifiable and clear and transparent and autonomous. You don't rely on a team to do their operations. What kind of data can be used? For instance, you can check the validator performance, their uptime, you can check geographic centralization. You will have a way to assign a score to different validators based on the data in history program, and then the Steward program will allocate the stake based on the score. Nice. And also, of course, there will be ways for governance to decide which strategy we want to use, tune some parameters. All of this is possible. Now, what's next? What can be built on top of Stakenet? There are several ideas that have been presented in this blog post, like having governance, don't have just one strategy and then governance decide which strategy to use, but maybe more strategies in parallel that are stake weighted. Then, depending on the support from governance on different strategies, then you can have ways to let different strategy optimizers show that the strategy is better. So competition based on different strategies to optimize the performance of a stake pool. You can also let users have their own very specific strategy only for their stake in some way. So, if some user, and even it can be for whatever reason, maybe a user want to stake only on specific validators that answer to specific criteria, like they have to be from this region, then they can do that. And what's next really is to extend Stakenet beyond the liquid staking and use it for any protocol that needs a way to allocate resources between different actors. So yeah, that's what's coming. That's what's Stakenet now and in the future. Next, the last article I have that I advise to read for this week is on Validator Economics from Ryan in the Helios blog. And this is a summary, and it's a nice, it's a reference, nice overview of what are the validator economics. So if you run a validator, what are your costs? What are your revenues? And what's the current status? So it was nice to read. It's a nice summary, and we have, in terms of cost, we have the hardware cost. You have to run hardware, um, and yeah, to give some order of magnitude of the cost, from Latitude, you will need to pay something around $370 to $470 per month. Then you have operational costs like voting. Yeah, we just said you have voting transactions, and this amount to around 1 sol per day that you need to pay. And then you will need to pay for bandwidth, and this depends on the service provider. So some are much cheaper than others. This is typically for the upload bandwidth, and you need to pay. And this depends also on the stake, because validators with a higher stake will be more involved, and in Turbine will do more work. And then for operational costs, also the node monitoring is definitely important. So you will have a team or people working on monitoring the node and ensure the uptime is there. And another cost is an opportunity cost, because you need to stake Sol. So you need to lock Sol that could have been used in other ways. So there is that, of course. What is the income instead? This is coming from Sol issuance, block rewards, and MEV. The issuance is coming from inflation, and inflation has predefined schedule, like it's decreasing over time, starting from high inflation, decreasing over time by a certain percentage, the same every year, going down to a lower bound of, I think, 1.5%, that will be there in perpetuity. It is distributed at the end of each epoch, and is depending on the stake and the uptime. Then we have lock rewards, because validators earn also from transaction fees. And you have 50% of the base fees and 50% of the priority fees going to the validator, while the rest is burned. And this is something that will change. We know already will change. It's not a good idea to burn a part of the priority fees. This should be incentive for validators. So it will be most likely 100% of priority fees going to the validator at some point. Otherwise, you can have like side deals, and that's not nice. And we have just seen in the first part of this video proposal of burning all of the base fees at this coming maybe at a later point, if coming. And last source of income would be MEV. And yeah, you have a nice dashboard here that you can check to see what kind of income is obtained through the Jito client. This is the schedule on inflation I was talking about. So you have a disinflation rate of minus 15% per year. And yes, this is the long-term inflation rate that will stay there in perpetuity, and this is 1.5%. So this is inflation without considering burning. So this is actual, let's say, is the issuance of the Sol token. And for MEV, yeah, we have this dashboard from Jito. You should just open it and explore. And this is just an idea of the profitability of specific bundles. Many bundles at yeah, near 0, 1 sol, and then the occasional. This is the period of 1 week. You cannot see more than 1 week actually, and you can see that sometimes there are highly profitable opportunities. And yeah, that's all I have. And until the next time, yeah, can't wait for the next Solana update. Thanks for listening, and yeah, until the next time. Ciao.